Welcome. There's a moment in every C++ developer's journey where they realize they've been doing something the hard way. For many, that moment is synchronization. Think of a mutex like a bathroom lock. Only one person gets in at a time, everyone else waits outside. Simple, but not every coordination problem is a bathroom. In this lesson, you'll learn the full toolkit: shared mutexes, semaphores, latches, barriers, and condition variables. Each one solves a different coordination problem. Let's learn to match the primitive to the problem. Before choosing a primitive, decide what you are protecting. Write one sentence that describes the invariant. Only one thread may mutate the cache at a time. At most, 8 workers may use the connection pool concurrently. All workers must finish initialization before any begins processing. The primitive should match the coordination problem. 4 common patterns. 1 shared object, use a mutex. A reader-writer data structure with frequent reads, use a shared mutex. A limited pool of resources, use a semaphore. A multi-step parallel phase, use a latch or barrier. If the invariant is unclear, the primitive choice will be unclear too. Start with the rule. Shared mutex allows multiple readers or one writer at a time. In this cache example, lookup acquires a shared lock. Multiple threads can read simultaneously. Update acquires a unique lock. Only one thread writes, and all readers wait. This is useful for read-mostly data structures where reads vastly outnumber writes. But a warning: shared mutex is not automatically faster than a plain mutex. The shared lock has overhead from atomic reference counting. If contention is low or reads are fast, a plain mutex may be simpler and just as fast. Measure before you optimize. Use shared mutex when profiling shows read contention is the bottleneck. A counting semaphore limits how many threads may proceed concurrently. Here we create a semaphore with a maximum count of 8, representing 8 database connection slots. Each worker calls acquire before doing a query. If all 8 slots are taken, acquire blocks until one is released. After the query, the worker calls release to free the slot. This is different from a mutex. A mutex models exclusive ownership, one thread at a time. A semaphore models capacity, up to n threads at a time. Use a semaphore when the question is how many, not who. Latches and barriers coordinate groups of threads. A latch is a one-time countdown. We create a latch with count 3, representing 3 workers. Each worker calls prepare, then count down. Then it calls wait, which blocks until the count reaches 0. Once all 3 have counted down, all 3 proceed to run. The latch fires once and is done. A barrier is similar but repeatable. Threads arrive at the barrier, wait for all to arrive, then proceed. At the next phase, they arrive again. Use a latch for one-time coordination like initialization gates. Use a barrier for iterative phases where threads must synchronize repeatedly. Condition variables remain the standard tool for sleeping until a state predicate becomes true. The pattern is simple: cv.waitOfLock, lambda, return, ready. The thread sleeps until notified, then checks the predicate. If the predicate is true, it proceeds. If not, it goes back to sleep. Always wait with a predicate. The operating system may issue spurious wake-ups, waking the thread even though nothing was notified. Without a predicate, the thread would proceed on stale state. Notify one and notify all are hints. They tell waiting threads to recheck. The predicate is the truth. The notification is just a nudge.
A quick comparison
Of the 5 primitives. Mutex, exclusive access to a shared invariant, one thread at a time, the default starting point. Shared mutex, mostly reads, rare writes, multiple readers or one writer. Measure before using. Condition variable, sleep until a predicate becomes true, the standard tool for producer-consumer and event-driven coordination. Counting semaphore, cap, concurrent access to a resource pool, up to n threads at a time. Latch, one-time group rendezvous, all threads count down, then proceed. Barrier, repeated group synchronization across iterative phases. Match the primitive to the coordination question.
Here's a worked example.
Using 3 primitives together. We have a job queue protected by a mutex and condition variable. A counting semaphore with a limit of 2 caps how many workers process jobs concurrently. A barrier with count 3 synchronizes the end of each processing phase. The condition variable waits for work to appear in the queue. The semaphore ensures only 2 workers run expensive processing at once. The barrier marks the end of a phase. All threads must arrive before the next phase begins. Most real systems don't need all 3 at once. The point is to match each primitive to one coordination rule instead of forcing a single mutex to model everything. 4 common mistakes with synchronization primitives. First, protecting different parts of one invariant with different locks. If 2 variables must stay in sync, one lock should protect both. Second, waiting without a predicate. Spurious wake-ups will break your logic. Always use the predicate form of wait. Third, holding a lock during slow I/O or long computation. Lock, update, shared state, unlock. Do the expensive work outside the critical section. Fourth, choosing atomics for a problem that really needs a larger shared data structure. Atomics protect individual variables. If your invariant spans multiple variables, use a mutex. 4 questions to choose the right primitive. If the question is, who owns access right now? Use a mutex. One thread at a time, exclusive ownership. If the question is, when should sleeping threads wake up? Use a condition variable. Sleep until a predicate is true. If the question is, how many workers may proceed at once? Use a semaphore. Cap concurrency to a fixed limit. If the question is, when does the whole group move to the next phase? Use a latch for one-time synchronization or a barrier for repeated phases. Ask the question first. The answer tells you the primitive. 3 exercises to build intuition. First, find a mutex-protected design in your code that really models a resource pool, several threads competing for a limited number of slots. Sketch a semaphore version and compare the clarity. Second, describe a staged parallel algorithm, like a simulation with setup, compute, and gather phases that would naturally fit a barrier. Third, pick one function that accesses shared data under a lock. Write down, in one sentence, the exact invariant that lock protects. If you can't name it, the design likely has a bug.
Here's the key takeaway.
A mutex is a bathroom lock. One person at a time, everyone else waits. But not every coordination problem is a bathroom. Some problems need a reader-writer lock. Some need a bouncer counting how many people are inside. Some need a starting gate where everyone waits until the whole group is ready. Match the primitive to the problem. For next topics, continue with advanced ranges and views to learn how to compose lazy sequence operations with the ranges library. Then, build systems and tooling for CMake, package management, and project structure. You now have the full synchronization toolkit. Use the right tool for each job. Thank you.